Hello everyone. We are looking into magnetic methods of subsurface investigation, right? In the previous lecture, we had seen some basic aspects of Earth's magnetism, and we had also had a look into what are the 5 components of Earth's magnetism. Then we had a look into what is magnetic susceptibility. So, this is the slide we had seen toward the end of the previous lecture. So, magnetic susceptibility is given by this relationship where I is the induced magnetism, which is equivalent to magnetic susceptibility and the strength of the magnetic force. Right. We had a look into this table in the previous lecture. That means the magnetic susceptibility of different rocks occurring in the earth is actually different, right? If you look at the different rock types, the magnetic susceptibility varies by an order of magnitude, right? And in general, magnetic susceptibility of massive igneous rocks is much higher than the other rocks, whereas the magnetic susceptibility of sedimentary rocks, which are the last 3, is comparatively lesser than the other massive rocks. This is what we are going to make use of in the magnetic exploration methods, right? And if you look at the magnetic susceptibility as we had seen in the previous page using a table, here it is very evident that the magnetic susceptibility of the basic igneous rocks are very much higher than all the other rocks which are up to this, right? These rocks has got comparatively lesser magnetic susceptibility, right? Among the other rocks, as I had just now told you, sedimentary type of rocks. Sedimentary rocks are having very low magnetic susceptibility. What does it indicate? These rocks do not have minerals that are magnetically susceptible, right? Whereas igneous and metamorphic rock are having minerals that are very much susceptible for magnetism. So, using the magnetic methods, we can very easily differentiate certainly between the sedimentary rocks and the other rocks, right? What do I refer by other rocks? That is metamorphic and igneous rocks. Among the metamorphic and igneous rocks, we are able to distinguish basic igneous rocks very easily because it has got very high magnetic susceptibility. So, this is a kind of a fundamental aspect of magnetic method. This is how magnetic method help us to differentiate rock types. Now, let us come to the instruments that we are going to make use of. Right. We had already seen there are 5 components of magnetic field. 2 are angles. One is known as inclination, that is referred by the letter I, which is the angle that the magnetic needle points, right, from the horizontal plane, right. Please look at my video, right. So, this is the angle the magnetic needle may point, right, depending upon the location where you are in the world, right, and the angle that it makes with the horizontal, which is referred as I, and the projection of this to the horizontal plane. This is the magnetic needle now, and the projection of this on the horizontal plane I am now marking in red color, right. The angle that the projected horizontal line makes with the geographical north is known as D. So, these 2 are angles, right, and all the other 3 are field vectors. The total field vector is referred by the letter B. It is the total field vector. Horizontal component of this field vector is given by the letter H, and the vertical component is referred by the letter Z. Most of the modern day instruments that we use for magnetic exploration measures the total field vector B, right. Usually they measure the total field vector. Instruments are very advanced and we need to achieve an accuracy or precision of at least 0.1 nanotesla, right. So, why we want to have 0.1 nanotesla? So, this is about one part of the background value, because of the fact everywhere there is going to be some magnetic strength which can be measured. As we have seen in the previous slide, almost all the rocks available in the earth are magnetically susceptible. Among them, the basic igneous rocks are having very high magnetic susceptibility, whereas all the other rocks including shale, clay is also magnetically susceptible. Hence, in order to differentiate all this, we need to have very accurate instrument with a precision of about 0.1 nanotesla. And the name of the instrument which we are going to use here is magnetometers. So, magnetometers are the instruments that are going to be used to measure any one of the 5 components which is shown in this figure. Most of it will measure the total field vector. The old magnetometers 20-30 years ago, we had magnetometers that consists of bar magnets, and it required accurate leveling, right. Those who have used surveying equipments, right, if you have used a theodolite, it is very essential to maintain leveling in the case of theodolite. Even if there is a minor error, there will be a huge error in measurement of surface topography, isn't it? So, very similar to that, even in the old magnetometers, leveling is very important, and we need to use stable platforms. However, recent geophones, especially very recent ones, have got advantage of carrying out measurements so quickly, instantaneously. We can take the reading with the coarse orientation, because the instrument is so much automated. It can even note down the latitude, longitude as well as elevation, right. They are all coupled using the differential GPS. So, modern day magnetometers are providing a facility that you can instantaneously take the reading without bothering very much with regard to the orientation, right. So, what are the advantages of these modern magnetometers? It is very easy to operate, and very quickly you can take the next measurement. That means cycling rate is very rapid, and the new reading can be taken within a gap of 2 seconds, right. Every 2 seconds you can take a new reading. That is what I am referring as rapid recycling rate. Modern magnetometers also have digital readouts, and they also have a facility. Every time we need not note down the reading in the field, it has got a inbuilt memory. So, simultaneously it will store the latitude, longitude or the station number, as well as the magnetometer readings will be automatically stored in the digital mode within the magnetometer. Later on, we can bring the magnetometer back to the laboratory and download the data. There are different types of magnetometers. We will briefly touch upon these types of magnetometers. They are flux gate magnetometer, proton precision or proton magnetometer, optically pumped magnetometer, lastly magnetic gradiometer. So, these are the different popular types only I have included here, popular types of magnetometers. Let us briefly see their functions. In the first one, flux gate magnetometer. In flux gate magnetometers, the cross section of or the principle of the magnetometer can be understood from this picture. Here there are two identical magnetic cores, right. They are bounded by coils. There are two coils. One coil is known as primary coil and the secondary coil. The dark black color is a primary coil and the light grayish color is the secondary coil. So, this is the arrangement with the center ferromagnetic core. These coils are wounded on opposite directions, right, and we will apply a current through the primary coil, right. In the field, by the press of the button, current will be applied to the primary coil, and when you apply current to the primary coil, right, when you apply current to the primary coil, the magnetic intensity that is prevailing at that particular place where we are making the measurement will result into development of certain signal in the secondary coil. That signal is proportional to the magnetic field strength of that particular location. So, this is how I can explain you very simply about the principle of flux gate magnetometer. That means the current or the signal that is going to be generated is proportional to the magnetic field that is prevalent at the place of investigation. Then the proton precision magnetometer, instead of a magnet here, we have a small container. This container is filled with some liquid such as kerosene or water, which is rich in hydrogen atoms, right. This vial is surrounded by a magnetic coil, as you see in this diagram, as well as here, right. And when the current is applied through this coil, right, with the help of a battery, right, these hydrogen ions realign themselves, right, forming a small dipole. As you see here, they are aligned in this fashion, aligning to the geomagnetic field, aligning along the geomagnetic field, right. And when these hydrogen ions align along the geomagnetic field, right, when you apply the current, their orientation gets changed. When you apply the current, as you see in the diagram below, which I have circled, then when I switch off the current, they try to realign themselves to their original position. This will trigger some electrical signal. That electrical signal is amplified and measured using a digital display, wherein it will be displayed. So, this is how we can understand the prevailing geomagnetic field at that particular place of our investigation. Then the next is a method in which this is known as optically pumped magnetometer. It is of highest accuracy as well as sensitivity. This consists of a glass vial. Previously, it was filled with the liquid, whereas here it is filled with some evaporate of metals, right, maybe cesium, rubidium or potassium. These evaporates in the form of gas will be energized with the help of a light. That is why it is called as optically pumped, right. Light of a particular wavelength, which we can understand in the next diagram. Right here we can see this is the vial containing the evaporates, right, and the light which is passed through this, which is of a particular wavelength. So, when the light is passed through this, depending upon the prevailing ambient magnetic field, the energy will be emitted and measured by the magnetometer. Suppose if the magnetic field is very strong over there, more energy is emitted and sensed by this meter, right, by this photocell, right. The photocell measures the energy, so the energy is much higher. When the ambient field is very weak, that means the magnetic field that is there is very less. If the magnetic field is less, the meter is not showing very high value, right. That means the cells, the evaporates which are here is so sensitive to the prevailing magnetic field, which is energized with optics, right. There is a source, a light which is emitting energy through this cell, and the energy received on the other side is also, there are some methods of amplification, and that is sensed with a photocell. So, wherever you have the very high energy, very high magnetic strength, the meter showing very high values. When the ambient field is very weak, it shows less value. So, this is how we make the measurement in optically pumped magnetometer. This meter is of very high accuracy, right. So, this accuracy we are able to achieve an accuracy of 0.01 nanotesla. So, the method in which we use optically pumped magnetometer, we are able to get results with high accuracy, right. A combination of two equipments, right, which we have seen so far. When you use two equipments, then it becomes a gradiometer. That means we have, suppose a person who is carrying can carry the gradiometer as you see here, right, with on either end you have a gradiometer or you have a magnetometer on either side. So, along your traverse, we are taking two successive measurements at closer, either vertical or horizontal measurements can be taken. So, this is gradiometer. So, these are the four types of magnetometers which are often used in magnetic survey. And as I had referred previously, modern day gravimeters also have an attachment of a global positioning system. So, this is able to connect with the global positioning satellites, right. With the help of that, we are able to precisely get the position established, right. That means you can traverse along a line, you can set the equipment to make measurements every few seconds or every few minutes or every few meters, right. As you walk, the magnetometer will automatically collect data at the preset distances or at preset times. So, that is the advantage of modern magnetometers, right. Now, magnetometer need to be calibrated actually before the measurement, because we want to make sure whether the magnetometer we have is working well or not. So, this is done by a Helmholtz coil. This coil will be used because this coil will generate some fixed magnetic field. We will place our magnetometer just above that to check whether the magnetometer is able to measure the magnetic strength produced by Helmholtz coil. So, this is how we calibrate the magnetometer before deploying it or before carrying out the survey in the field. Just before the survey, we need to calibrate. Suppose if the meter is not showing the expected value, then there is a provision in the magnetometer, right. There will be a adjusting screw or some other method depending upon the manufacturer. Let us at least understand there is a provision provided in the magnetometer. Using that provision, we can adjust the meter to show the value that was expected out of the Helmholtz coil which we are using, right. After making this calibration, we will repeat the measurements using the Helmholtz coil or vary the magnetic strength that is generated from the Helmholtz coil and recheck, double check or triple check to know whether our magnetometer is working well or not. Then magnetometer need to also be checked for diurnal variation. That means it is a instrument. So, instrument will have an error due to changes in time, right. So, it is preferable, or we need to carry out what is known as diurnal correction during the magnetic survey. So, during magnetic survey, right, we need to carry out a continuous measurement of the magnetic field strength at a particular station, right. So, with the help of that, the data can be corrected for diurnal variation. How do we do that, right? Let us, I will mark, this is the time axis. This is the area of our investigation. This is a map, right? These are all the points at which we are going to measure the magnetic susceptibility or magnetic total field using the magnetometer. We will choose one station as a base station, preferably the station which is easily accessible. Right. During the survey, we will visit this site, let us say every 20 or 30 minutes. So, we are commencing our survey here, first point, second point, third point. So, then we go here, take the measurement, then come back to this place, continue our survey, right. Then after 30 minutes go, come back, continue our survey, then come back, right, go back, then again visit this site. The idea is you collect the time versus total magnetic field. So, this is known as diurnal curve. So, why are we collecting this information? This diurnal correction is need to be applied to the magnetic data, right. Let us imagine we started our work at 6 a.m. This is 6 p.m. right. So, within a day there was some minor variation in the magnetic field intensity at the same place. The same will also be happening at all our magnetic stations. So, all our data has to be corrected as if they are taken at the same time, right. If the diurnal correction, if the variation within a day is, if the diurnal correction is not more than 15 to 20 gammas or nanotesla over an hour, then we need not apply diurnal correction. When the variation in the diurnal curve which we have prepared is greater than 20 nanotesla, then we need to apply diurnal correction, right. And generally the diurnal correction or the diurnal curve need to be approximately linear, as I have drawn here, right, approximately linear over time. It should not show extreme variations, something like this, right. If it is showing extreme variation, it is advisable not to carry out magnetic survey during such times. We have to wait, right. Then what is the other correction we need to apply? Then the next is the latitude correction. Hope you can recollect. In the previous lecture, we had seen the magnetic intensity vary from equator to the pole. So, during our survey, let us imagine this is the map, this is the north direction, and imagine the distance between north to south of our study area is 200 kilometers. I am just assuming as 200 kilometers. So, there will be expected variation in the magnetic field strength from here to here, right. Here it will be less and here it will be more, because equator is here, pole is somewhere here, because that is the north direction, right. Let us imagine equator is here and this is the north direction, this is equator, right. So, value which we measure using our magnetometer is expected to be comparatively less here than this particular place. Why? Because this place is very much away from the center of the earth in comparison with this location. So, we need to apply latitude correction too, right. How can we apply latitude correction? We know very well with respect to latitude how the magnetic field strength is going to vary. Using that, we will carry out the correction for latitude. Then elevation and terrain correction. Elevation and terrain correction which was given in the gravity methods, whereas in magnetic methods it is really difficult to understand what is the elevation and terrain correction, right. So, generally in magnetic methods it is difficult to estimate, hence we do not apply this elevation and terrain correction. So, these are all the corrections that need to be applied. Now, let us see how we can carry out the survey in the field. Survey in the field can be carried out in all these three ways, right. That is the greatest advantage of magnetic methods, which is similar to that of gravity methods, right. We can carry out investigation from ground or from air or from water also, from a lake or from a ocean, we can carry out the survey. Previously, we had seen electrical methods. Electrical methods can be carried out only on land. Only gravity and magnetic methods can be carried out from land, from air as well as from on water, right, from a ship. Right. That is the greatest advantage of magnetic methods. Right. What is for ground magnetic survey? Normally, ground magnetic survey is performed over smaller areas. If our area of interest is very less, we go about in doing the survey by ground based method. Right. Usually, the spacing between the stations, it is always tricky to decide what should be the spacing between the locations where you are going to make the measurement of magnetic field strength, right. So, that depends on the objective of our survey, always, isn't it? So, what is the aim of our survey? Are you looking for a buried artifacts? Are you looking for a buried steel drum? The size may be very less, or you are trying to understand how the depth to the basement rock varies over the surface of the earth, or are you searching for a thick sedimentary basin, right. Obviously, our resolution of survey, not only in this method, in all the other geophysical methods also, what should be the distance at which we want to collect information depends on the aim of our survey, right. Suppose if you are searching for a artifact or some buried treasures of dimension 1 by 1 by 1 meter, then the station spacing has to be very, very small, isn't it? Maybe 5 or 10 meters. Or you are searching for a sedimentary, thick sedimentary basin where the thickness of the sediment is expected to be 4 or 5 kilometers, then the station distance can be much higher. In fact, we can go in for aeromagnetic survey too, right. So, generally in ground based survey, station spacing will be between 10 to 100 meters. And we need to take sufficient care, since magnetometer is a very sensitive instrument, right. It is able to measure to the level of 0.1 nanotesla or 0.01 nanotesla. The magnetic reading will also be affected by the presence of iron next to the magnetometers, right. Suppose if our station is nearer to a railway line, it will have an impact on our reading. So, we should not locate our stations, right. If these are the stations, we should take care that our stations are at least 50 meters away from the railway lines or an automobile or roads, right. In roads also we have brought in some large amount of massive rocks. The aggregates used in the tar is rocks. We already know rocks has got high magnetic intensity, right. So, we have to be cautious. There should not be any fencing or urban area. In urban area, it is nearly practically impossible to go for magnetic method of surveying, right. So, a magnetic method of survey actually progresses more rapidly than gravity survey, right. In gravity survey, we need to make some other additional care. We need to take some additional care with regard to fixing the gravimeter on the surface, whereas in magnetic methods, even coarse, as we had seen, modern day gravimeter is able to overcome all these errors of not keeping the instrument horizontally. So, magnetic survey is much more rapidly carried out than the gravity survey, right. So, as you see in the diagram, right, magnetic survey is carried out in a grid manner, right. Maybe as you can see here, it is just a map, right, more or less like here, right. In every grid you can take one measurement, right. So, magnetic survey is normally carried out on a grid pattern. Sometimes gravity survey is carried out along a traverse, right. Along a line we conduct measurements. So, these are the two ways. One is grid pattern, the second is along a traverse. This is how we carry out the work in the field, right. And we have seen already, right, the presence of steel or iron material near to the magnetometer will affect the data, right. So, we have to check ourselves whether we are magnetically clean, right, whether we are wearing maybe belt made up of buckles, buckle of the belt might have been made up of iron. So, all these things have to be avoided, they have to be removed. So, a compass should be at least 3 meter away from the magnetometer. Suppose if you are using a magnetic compass, even that compass should be at least 3 meters away. How can we make sure that this is the station where you have put the magnetometer, it is showing some display? How you make sure that you are, as a person who are in the field, to check whether you are magnetically clean? So, this can be done like a final test. You immobilize the magnetometer and then start taking the reading from the magnetometer, right, so that the operator moves closer or moves away or goes around the magnetometer. Just by looking at the reading, just walk around the magnetometer and check whether the reading shown by the magnetometer is changing or not. If it is not changing, then you are considered to be magnetically clean. If it changes, maybe some part of your cloth or some part in some part of your body you have some magnetic material. That is why the value changes when you walk closer or far away or go around the instrument. Okay, this is how we check and then we carry out the survey.